How did a tiny Martian lander become one of the most important planetary science experiments in history? On the 26th of November 2018, NASA's InSight lander touched down on the surface of Mars, on a wide, flat plain called Elysium Planitia. Unlike Mars rovers, InSight wasn't designed to move around or explore the surface. Its goal was simply to sit and wait, to listen, with the most sensitive seismometer ever placed on another world. It was trying to detect seismic waves on Mars in an attempt to decode the planet's interior structure. For the very first time, scientists could begin to decipher what lies beneath the surface of Mars. And what they found was lumpy. I'm Alex McColgan, and you're watching Astrum. Join me as we unearth secrets that Mars has kept buried deep beneath its surface for billions of years, and get to the bottom of how this chunky planetary interior may be reshaping our understanding of all the rocky planets in our solar system and beyond. We live in a solar system with 4 terrestrial or rocky planets: Mercury, Venus, Earth, and Mars. 4.5 billion years ago, these planets formed from the same primordial cloud of dust and gas. Yet each world is distinct, and for the most part, our understanding of their interiors has been a slow process. That is, until now. Mercury is a scorched, dry planet with no atmosphere, its surface battered with craters. Venus is a hellish place, like a pressure cooker wrapped in suffocating clouds of sulfuric acid. Earth, of course, is teeming with water, life, and a protective atmosphere. But how it became like that is, even now, somewhat of a mystery. What we do know, however, is that the interior is constantly churning, recycling crust and replacing it, effectively erasing much of its own history through the movement of tectonic plates. We simply don't know what the inside of our planet actually looked like millions of years ago. But Mars? Well, Mars has been doing something entirely different. This cold, quiet planet has a thin atmosphere, and its surface appears to be frozen in time. While Earth has been erasing history, Mars has been preserving it. It turns out that preservation also extends below the ground to the Martian interior. This makes it, arguably, one of the most valuable sources of information in the entire solar system. It's a time capsule of planetary formation, explaining not only how Mars came to be, but all rocky planets, including Earth. The inside of the red planet could help explain the role our own planet's interior played in creating a habitable world. The question is, how do you explore the insides of a planet? We know plenty about the surfaces of the other rocky planets in our solar system because we can see them with telescopes, with orbiters, with landers. Their internal structure, however, is another thing altogether. But why? On the surface, the answer seems obvious, and yes, I really did mean to make that joke. You just can't see inside a planet. But the problem is actually much deeper. Let's look at the Earth for some perspective. Our planet's inner core reaches a depth of about 6,378 kilometers from the surface. Let's say we wanted to learn about Earth's interior by drilling down as far as we could reach. First, we'd have to make it through the crust, and depending on where we started drilling, that could be anywhere from 5 to 60 kilometers thick. If we made it that far, we would reach the mantle. Not only would our drill have to withstand the temperatures of up to 1000 degrees Celsius, it would also have to pass through another 2,900 kilometers of mantle to reach the outer core. From there would be another 2,200 kilometers of liquid outer core and 1,250 kilometers of solid inner core made of high-density metal, reaching temperatures of up to 6,000 degrees Celsius before we reach the center. Of course, this scenario is impossible. Not only would our tools melt or vaporize at such temperatures, but even with our best efforts, The deepest humans have ever managed to drill down into the Earth was only a little more than 12 kilometers at the Kola super deep borehole in Russia. It took 22 years, from 1970 to 1992, to make it that far, and drilling had to stop when temperatures became too extreme at 180 degrees Celsius. They had made it about a third of the way through the crust where the borehole was located over the Baltic Shield continental crust. We did make it to the Mantle once. In 2023 and 2024, a team aboard the Joyda's Resolution drilling ship managed to find a piece of crust thin enough to drill down more than 1,200 meters deep and retrieve a sample of rock from the mantle. But they had to do this in the middle of the Atlantic Ocean, at the top of an underwater mountain more than 700 meters under the sea. No easy feat. As you can see, physically accessing our own planet's interior is hard enough, so unlocking the contents of other rocky planets' interiors is that much more challenging. And without access to their interiors, we're missing out on a treasure trove of clues. It's not just for our scientists to solve problems like this. One day, the next generation will have many such problems, both on Earth and on Mars. So giving them the knowledge they'll need to do so now is critical. And how better to do that than with Brilliant, the sponsor of today's video. Brilliant is a cutting-edge personal tutor that helps any student excel in math, science, and coding. We know that one-on-one tutoring can make all the difference when it comes to student success. Sadly, teachers in classrooms don't always have the time to go over tricky concepts if something isn't making sense. And when students turn to AI tools, most just hand them the answer instead of helping them build real understanding. That's where Brilliant comes in. It guides students to their own aha moments by asking probing questions and by breaking problems down step by step. When I've tried Brilliant out myself, it actually drew on my screen to highlight key points for me to think about. I always found I learned most when I had someone there to help guide me through my studies when I was younger. So why not give Brilliant a try and see if it can do the same for your kids? To check out what Brilliant has to offer, scan my QR code or click my link in the description below, and Astrum users who do so can get 20% off upgrading to a premium subscription. Now, back to the problem at hand. Why do rocky planets have dramatically different core sizes? How exactly do the different layers of a planet's interior separate? What makes some planets tectonically active and others not? How do interiors impact a planet's ability to retain an atmosphere, maintain a magnetic field, hold liquid water on the surface, or support life? These questions have profound implications for habitability, and the answers could rewrite our understanding of both our own solar system's past and how extrasolar systems form with rocky exoplanets of their own. But thankfully, there is another way to probe the insides of a planet. Now, as difficult as it is to study a planet's interior, here on Earth at least, we have managed to decode what it's like right now. And that's most importantly thanks to seismometers, instruments that measure seismic waves. When an earthquake happens, it sends ripples of energy in every direction. These seismic waves travel at different speeds depending on the density and composition of the material the waves are traveling through. There are two main types of waves, one called P or primary waves and the other called S or secondary waves. As you can see, when P waves encounter different layers inside the Earth, the different materials cause the waves to change speed and direction, but the waves are still able to travel through all the layers. But when S waves encounter the liquid core, they can't travel through that material. This is because of the shape of the P and S waves themselves. P waves move by compressing and expanding the material they move through, pushing and pulling like a slinky. They're called primary waves because they move faster than S waves. These P waves can travel through both liquid and solid materials, making them capable of passing through Earth's core. S waves, on the other hand, move by shifting the material they pass through from side to side, or up and down as they pass through. This type of wave can't travel through a liquid. By measuring and recording P and S waves around the globe, we get a sort of seismic X-ray of Earth's interior. The way the P and S waves speed up or slow down, and how they bend, refract, or get blocked by different layers allow us to outline what it looks like inside the planet, what layers there are, if they are solid or liquid, and can even offer clues about the composition of those layers. But Earth's interior is too active for us to understand much about its past. The continually recycled interior makes it extremely hard to work out the original conditions of how our planet formed. Mars, on the other hand, happens to be a sort of Goldilocks world for studying the interior of rocky planets. It's very nearly geologically dormant, but was active enough in the past to develop a crust, mantle, core, and to be volcanically active. Critically, the majority of Mars's geological activity slowed down to a near stop, in time to preserve its interior structure roughly 3 to 4 billion years ago, like an insect that got stuck in amber, frozen in time, and preserved for centuries. This likely happened because Mars is significantly smaller than Earth, about half the diameter, and only about 1/10 of Earth's mass. Smaller planets cool more quickly, like a small cup of tea will cool faster than a large teapot full. As it cooled, Mars likely lost most of its internal heat within 8 billion years of forming, becoming a mostly quiet and cool planet. Because of this, the interior of Mars is closer to a primordial state than anything we can study on Earth. It's a record of what a rocky planet can look like after the interior has separated into layers, but before billions of years of tectonic recycling destroys the history. And therein lies the key to why Mars is so perfect for studying planetary interiors. Its internal activity nearly stopped, but not entirely. That makes Mars both a geological time capsule and a planet capable of producing low-level seismic data that can reveal its contents to us. A winning combination, if we can measure it. For decades, all we could do was study Mars from the surface, from orbit, or from Martian meteorites that eventually found their way to Earth. But we couldn't do seismology on Mars. That changed on the 26th of November 2018, when NASA's InSight lander, which stands for Interior Exploration Using Seismic Investigations, Geodesy and Heat Transport, touched down near the Martian equator. The location was chosen for its flatness, stability, and lack of rocks. This would give InSight the best chance at successfully deploying its sensitive instruments and then listen, unmoving, silently for years. InSight was carrying the Seismic Experiment for Interior Structure, or SEIS, a seismometer primarily built by the French space agency CNES as part of an international collaboration. The seismometer worked by using electrodes to measure the displacement of the moving parts of its pendulum, making for an astonishingly sensitive instrument. At the time it was deployed, SEIS was the most sensitive seismometer ever put on another planet. It was sensitive enough to detect ground movements smaller than the diameter of a hydrogen atom. The execution may have been complex, but the idea was simple. Put the lander on Mars, deploy the seismometer on the Martian surface, and wait for Marsquakes, the Martian equivalent of an earthquake thought to be mainly caused by the cooling and shrinking of the planet's crust, or in the volcanic regions, ongoing magma movements deep underground. The next part of the plan was to record the seismic waves and use the properties of those waves to map the interior of Mars, similar to what's been done on Earth. Of course, some wondered if Mars would even have quakes. Maybe it was too geologically dead. Would InSight end up listening to a completely silent planet? Well, no, as it turns out. Mars was not silent. In fact, InSight began detecting Marsquakes shortly after SEIS was deployed, with the first quake recorded on the 6th of April 2019 on the lander's 128th Martian day, or Sol. This quake was too small to provide information about the interior, but it was a promising sign of more to come. By the time dust-covered solar panels and dark skies brought the InSight lander's mission to an end in 2022, it had recorded more than 1,319 Marsquakes, including a magnitude 5 quake on the 4th of May 2022, the 1,222nd Martian Sol. Whilst on Earth this is a relatively medium-scale quake, on Mars it's pretty much as big as scientists predict they can get, and we detected one. InSight also carried out a radio science experiment called the Rotation and Interior Structure Experiment, or RISE. It used precise radio signal tracking to measure Mars's slight wobble as it rotated, called its precession. The wobble is primarily due to the gravitational pull of the Sun and other planets, particularly Jupiter, but is also sensitive to the distribution of mass inside a planet, which could provide further constraints about the interior structure, specifically the core. Together, these instruments gave scientists an unprecedented look into the Martian interior, and although the lander's job concluded in 2022, we continue to learn from all the data it collected. Before InSight, we knew very little about the interior structure of Mars. Estimates about how thick the crust was on Mars ranged from anywhere from about 20 kilometers, similar to our own Earth crust thickness, all the way to 100 kilometers, depending on the method used and assumptions made. Seismic data from InSight helped dramatically narrow down this estimate, which is now between 24 to 72 kilometers thick on average. And below the Martian crust, made up of iron, magnesium, aluminium, calcium, and potassium, is a rocky mantle that extends to a depth of 1,560 kilometers. And then finally, we get to the dense Martian core made of iron, nickel, and sulfur, stretching about 1,830 kilometers in radius. Plenty of interesting findings have come from the InSight data, one of which is that Mars seems to have a crustal dichotomy, a dramatic difference between the crustal thickness in the northern and southern hemispheres. The north has low-lying plains with thin crust, while the south has heavily cratered highlands with thick crust. But the origin of this difference is still being investigated. Perhaps the most unexpected and unusual find to emerge from the InSight data is that the interior of Mars is lumpy. And no, before you wonder, I'm not joking. In 2025, a team of scientists published their results in the journal Science, fundamentally changing our view of the Martian mantle. Using seismic data from InSight, they found that Mars's mantle is far from uniform. In fact, they found it wasn't smooth at all. At first, the team wasn't sure what they were seeing until they realized that the seismic waves were slowing down at specific regions scattered throughout the mantle. They found significant regions where the composition, temperature, and structure differed from their surroundings, painting a picture of a mantle that is patchy, irregular, and more complex than many models had predicted. These irregular lumps or chunks are what appear to be the leftover fragments from catastrophic ancient impacts that happened as Mars was just forming over 4.5 billion years ago. These could have been giant asteroids, large protoplanets, or some other type of rocky debris. The early solar system was full of it. There's no way to know which of these sources they came from, but their remains definitely still exist, trapped in the Martian mantle, some as large as 4 kilometers across. The paper's lead author, Konstantinos Haralambous of Imperial College London, said the pattern of these lumps was kind of like shattered glass, with a few large shards and many small ones. These ancient impacts would have released enough energy to melt whole continent-sized swaths of the early crust and mantle into oceans of magma. Those impact fragments and Martian debris got injected deep into those vast magma oceans, which later cooled, trapping the ancient debris deep in the planet's interior. It may also have implications for the volcanism on Mars, which created some of the biggest volcanoes in our solar system, like Olympus Mons, which stands nearly 22 kilometers above the surrounding Martian plains. Perhaps an uneven distribution of heat-producing elements helped drive volcanism in certain regions. And because Mars doesn't have active tectonic activity, its interior has been able to hold onto those chunks like a planetary time capsule, waiting 4.5 billion years for InSight to find them. We actually have another piece of evidence that points towards this being true. Usually volcanoes are very dense, but gravity studies of the area around Olympus Mons shows that the entire surrounding region, known as Tharsis Rise, is unusually high and surrounded by an area of comparatively weak gravity. For a while, this baffled scientists, but in 2024, a multi-mission study led by Bart Root of Delft University of Technology came up with the answer. They found a mass 1,750 kilometers across and around 1,100 kilometers below the surface. It's incredibly light, which is giving the entire Tharsis region a boost upwards. They believe it could be a huge lava plume traveling up to the surface. Perhaps this volcano isn't as dormant as we thought. They don't know what caused it, but Mars's chunky interior could play a part. But the bigger question is, what does all this mean for us? These studies show that Mars had a violent early history and that its mantle evolved sluggishly over billions of years. It's likely that something similar happened early in our planet's history too. We just can't see the scars with our churning interior. This finding is also forcing scientists to rethink their models of planetary evolution in general. They now think that other planets without active plate tectonics like Mercury and Venus may also have lumpy interiors. Only time will tell. Beyond that, this has, as ever, raised more questions than it's answered. How is it that these clumps remain in the mantle? And what impact do they have on the planet's future? Why is it that Earth's mantle kept churning where others didn't? Is that key to making a planet habitable? The Martian lumpiness is like a fossil record of early planetary formation and processes, and a valuable lesson about a period of development that other rocky planets may have also experienced. Now we can use this data in history as a reference point for understanding other planets that we may never be able to put landers on. If we can better understand what processes created the chunks inside of Mars, then we can build models of those processes and hopefully start to answer some of the questions this discovery has created. InSight has given us a remarkable start, and more discoveries are yet to come. As for other planets and habitability beyond Earth, well, first we need to get probes on other planets in the solar system. Beyond that, who knows if there's another remote sensing method we could use to test what the interiors of exoplanets may look like. Maybe one day, it could be a way to work out which planets are most likely to host life. But not quite yet. For now, I'm content with imagining Mars as more like a Snickers than its chocolate namesake. In other words, we've got a long way to go. Patreon members got access to this video ad-free, and more importantly, they keep Astrum grounded in a community passionate about space, not just YouTube AdSense and algorithms. So sign up with the link in the description. Being a member means you're part of the reason Astrum can focus on the kinds of videos people actually want to watch. It's where our most engaged viewers are, people who care about learning, exploring, and seeing what's out there. If that sounds like you, join the Astrum Patreon today and be part of where we're headed.